Hi guys, so welcome back to VLSI 101. So our goal is to build our own processor. So you all completed your week one tasks. So that was to get into the MIPS assembly. So this week's task was to build the data path, get started with the data path and understand the various blocks for the MIPS data path. Hope you all had fun trying it out. So let's go through what we have put for tasks for this week. So first was to install the Keras Verilog. So you can just look into the, if you're using Linux, you can just go through the blog. So whether it's just like two commands away. So for installing both GTK Wave and Keras Verilog, and or if you're using Windows, you can go through the official documentation to install it. Okay, so that was the first thing that we needed to do for this week, and then to go through the architecture, the instruction types in the book. The page numbers have been mentioned here. So if you would have gone through, you would have had a basic idea of the MIPS instruction set and its basic architecture. Okay, so and then we were supposed to build the basic blocks of the data path. Okay, so that was it. So using this data path first, this will create a foundation for R type instructions. So that was the goal. And apart from that, okay, we are logging the results. Okay, fine. So let's move on to the main part. Okay, so what are the core elements inside the MIPS core architecture? So let's look into that. So first we have the program counter. Okay, that just stores the next instruction to be executed. Instruction memory, it contains all the instructions which are to be executed. Okay, register file. Okay, this is for operating with the doing the operations. Okay, ALU control unit, main control unit, data memory, top module. Okay, so first we will have to build these blocks, then only can we instantiate them and build the data path. Okay, so first let's look. This thing is actually available from the book itself. We have documented it for quick view. Okay, so okay, first let's look into the architecture, the data path. It might be overwhelming, but it's okay, it's fine. Okay, where's the diagram? Yeah, I think even this should do the trick. Okay, so for building the blocks, just by looking into this, we can tell instruction memory, registers, ALU, data memory, ALU control. Okay, wait, this is not the block. Yeah, you can look into this instead. Yeah, so we have the instruction memory, registers, program counter, ALU, data memory, ALU control unit, and the main control unit. So these are the main blocks. Okay, so this is what we are going to show now. Is just one way of implementing it. We can build separate modules for each of these as well. So this the one that we are going to show now is just one way. Okay, so just by looking at this, these are the blocks that we have considered. So this and this. Okay, so we are building that and we'll test it. Okay, using and the test bench. Okay, so just by looking into the blocks, we can say what are the input and output ports for this. So for instruction memory, we read the address, and from that we get the output as instruction. So that's clear. And the input to the control unit is the instruction, and the output are the various controls to the various blocks. Okay, you don't have to memorize them, just look into it. Okay, and then for the register file, which has 32-bit registers, so we can see that the inputs for this are read register 1, 2, write register, write data. So the outputs for this file are read data 1, read data 2. Okay, so this is okay thing. Okay, we're just giving the register number and following with the value in that register. Okay, to write the value, we're passing it through the number of the register that we're going to write into, and the data that we're going to write into that register. Okay, okay, so similarly we get the output, okay, from the file ALU. So the two inputs A and B, and one output is 0 and the another output is the result, depending upon the operation. Okay, we all know what an ALU is. Okay, and then the inputs and outputs for the data memory, address and write data, the output is read data. Okay, so I think that's clear. Okay, so I'm just explaining you the output and input ports. And similarly, for the ALU control, the input is ALU op from the control unit, and the output it's a 4-bit value that is passed to the ALU. Okay. Okay. So first, the most important block is the ALU that actually does the computation. Okay. So let's look into the instruction set. Okay. What are the instructions that are available? Okay. The arithmetic instructions. So just by looking into it, you can just guess what are those: add, subtract, add immediate, and, or, nor, all the immediate. Or they all are arithmetic and logical instructions. Okay, so we'll all these operations will be done within ALU. Okay, so remember the instructions: add, subtract, and, or, nor, shift left logical, shift right logical. Okay, so these are the instructions. And apart from that, we have these set on less than and set on less than unsigned as well. As you can see, they are also an arithmetic type of instruction. Okay. Okay. So fine. Okay. So I guess this explanation is enough for now. Okay. So we understood the basic blocks, the input and output ports for the blocks. So let's look into the code there. Okay. Okay. So we have done it here. We'll just test each of the blocks. So we'll just provide you a sample of what we've done. Okay. Okay. So first let's open our ALU. Okay. So I'm using VA for opening it. Okay. So this is our ALU. Okay. So this is a test bench. Okay. Fine. So as you can see, the two for the module ALU, what are the things that we are defining? We have defined the input wires A and B, and the control obviously, which will come from the ALU control, and the results output, the ALU result, and 0 when the result is 0. Okay. So and we also have signed and unsigned instructions here, so we have included that as well. Okay, for differentiating between signed and unsigned input values to the ALU. Okay. So whenever there's a change in any of the signals, this block will get executed. I know I hope you all are familiar with Verilog. Okay. So this is just an always block. Okay. Whenever there's any change in value, so we'll execute this block. So depending upon the control value that we get from the ALU control unit, so we'll be doing these operations like we have marked it here for easier understanding: and, or, add, subtract, set on less than, signed, unsigned. Okay. Okay, we have mentioned that. Okay, nor, XOR, shift logical left, shift right logical. Okay, shift right arithmetic. Okay, this is an arithmetic shift. Okay, apart from that, the table that we showed, we have implemented XOR and arithmetic right shift as well, but that's fine. Okay, so we have done this. Okay, and whenever the result is 0, we are turning 0 to 1, the 0 variable to 1. Okay, 0 port to 1. Okay, fine. And then this is the basic design for ALU, and then followed by the test bench. Okay, so you just define the time scale here. This is up to you if you want it or not. This is just for simulation purposes, that's optional. Okay, fine. And then for writing a test bench similarly, so this will be on top of the module. Okay, so inputs will be passed from the ALU and the outputs will be observed. Okay, so instantiating the ALU block, and then we have just mapped it with the corresponding ports. So following that, we have put an initial block. This is a dump file. Okay, this will be the file that we will be using to look into the waveform. Okay, so we need to add this block, and then followed by the tests. Okay, what are the tests that we have added? We've just given input values. Okay, the inputs and the control unit. So what is this? This is for add, this is for subtract, this is for and, or, set on less than, XOR, nor. Okay, SSL, SLL, SRL, SRA. Okay, so and then we have finished the test bench. So this is a very basic test bench that we have done. So I think you all have got a basic idea of this. So let's see how to run this and check if it's working. Okay. Okay, so we have it here. So to run it, so this is the command. After installing, we use this. So Verilog. So we define the output file. Okay, so we give our design file and the test bench. The order doesn't matter. It's okay. it doesn't matter. Okay, so what this does is basically just checks for syntax errors in all the Verilog files. Okay, yeah, okay, it's more like that. It's not actually running the program, it's just basically checking if there are any errors in the code. So as you can see, there are no errors in our present code, so there are no issues with that. And then like let's compile the code, let's run it to the test bench, the values that we given, let's test it with that. Okay, so ALU test, okay, we have named it that way, so okay, we run it. Okay, as you can see, we have generated the dump file now, so we can view the waveform, okay, of our analysis. Okay, let's just copy that. Okay, I've separated the various tabs so that it will be easier. So GTK wave, let's just clear first. GTK wave. Okay, we have copied the file. Let's open it. Okay, so as you can see, we have opened the file. So okay, we insert. Okay, and then let's just open it properly. Okay, yeah. So as you can see, for the various inputs, first what did we do? We performed add. So as you can see, A plus 5 is F. So just by looking into the waveform, you can see what's happening, and it's easier to visualize. Okay, you can see all the operations that are happening, the same ones that we have mentioned in the test. So this way you can like debug it. Okay, I hope that was clear. So let's look into some other block as well. Let's look into the ALU control. Okay, ALU control. Let's open ALU control. Okay, this is our control unit which controls the ALU. Okay, now let's leave this. Okay, TP. We don't want ALU TP. We want control units just. Okay. Okay, we got it. Okay, again, so what are the input and output for the AL control unit? So the input is, we have the ALU op coming from the control unit as we checked, and apart from that we also we need the funct. Okay, so funct, I think you're not familiar with this. Let me just we look into the data format, the instruction format for R type. Okay, yeah, just a quick look. Okay, so funct is basically for R type. Okay, this opcode will be all zeros. Okay, so this funct is what defines what arithmetic operations that we're doing. Okay, so, in a nutshell. Okay, just keep that in mind, and then let's check this. Okay, so we get that. Okay, so we have again inside an always block. So any change in the input, it's a combinational block. Okay, so inside that, as you can see, we have put various cases for ALU operation that is coming from the control unit. So if it's 1-0, we're considering it as an arithmetic R type. Okay, all the arithmetic operations basically. Okay, so inside that, as you can see, for various values of the funct field, the ALU control is set for add, subtract, and or. So that is what we're doing, and for by default we're setting it to AND. That is okay. I hope this is clear. We'll just quickly go through it. Okay, and the test bench as well. So the inputs that we set here, we have defined it again here. However, we'll be passing the values through this. Okay, so and we'll be checking the output. Okay, and we are instantiating the block again, the dump file, code for dump, and then what are the values that we given. Okay, we have tested all the possible ALU op from the control unit. Okay, that we're getting. So this 1-0 case is what we are interested right now, but future we'll be doing that. For now, that is why we've just put it as XX. Okay, like I don't care. Okay, so as you can see, we have trying to check all the cases whether it's coming up perfectly. Okay, fine. So I think it's clear. So let's just run it in the same way that we did. So instead of that, I'm too lazy to type it out, so I'll just leave somewhere here. Yeah, okay. So these are files. Okay, so we're defining the output file. These are the two. This is the test bench and the design file. Okay, Okay, this is just for checking the syntax and all the other things. Okay, there are no errors. So what we're doing is next we're going to run the test. Okay. So we have generated the .vcd file, the waveform file, again in the same way. Okay. Now let's just again, I'll close that gtk wave control dp. Okay, so we are opening the vcd file for that. Okay, let's see, as I can see. So for the first two instructions are load and store and those things, we had given the output as XX, and as you can see the waveform as well, we are getting that. Okay, and also you can add the $monitor to print out the values. Okay, I haven't added that, but you can do that. Just the $monitor and what are all the variables that you wish to display, you can do that. We'll get that, you'll get the values along with the timestamp. Okay, so it will be easier for debugging as well initially, and just you can write that value into a text file. Okay, okay, if needed, that you can do it if it's needed. As you can see the values, see, for the corresponding the signal we're getting this value, this ALU control, which will be given to the ALU. Okay, so similarly we can see all the other designs. Let me just, so as you can see what and all have we done. So you can see the control unit. Okay, let's just open the control unit. You have to do the other tests similarly in this way. Okay, as you can see, control unit is like somewhat complex because we haven't included any of these instructions yet. Okay, so for the R type, so if you went through the book properly, you notice these fields, the output. So ALU we just went through, right? It's basically the control unit for the ALU control unit. Okay, I think that is clear. Okay, jump branch is for those instruction, and memory to memory is for enabling read and write from the data memory. Okay, read write is basically to write the value result what you are getting into the registers. So yeah, these are the ports. If you go through the book, it will be clear to you. So this is just another example of what we have done. And then if you wish to look into the test bench, if you want to look into the test bench, let's look at it. Oh, sorry, my bad. I missed it. Okay. So similarly, for all the cases, you just checked it. It's not that much of a big deal. You can try it out. Okay, and I'll just show you what I've done. What are all the designs? See, so as you can see, we have the data memory as well. What have we done in the data memory? Oh, sorry, my bad. Okay, so this is a data memory. So we are basically reading from a hex file that is available in our design. Okay, so we are defining the area. Okay, I don't know, 1 KB. Yeah, so it's just a way you can do it. Okay, what have we done here? We are reading the file, X file. Okay, let's, you can look into the data hex file as well. We've just put values. This is just a X file and you put the values. Okay, just by reading it you can like store it, so you can mimic the actual like how the memory would be, a flash or a non-volatile memory. Okay, just mimic that. Okay, so and then next, instruction memory. Okay, instruction again. Instruction memory is the same thing actually, similar to data memory. Okay, I missed the V again. Instruction memory dot X. Yeah, so we just put here some values for sample. Okay, we'll be reading this, and this values These are the values that will be actually stored in the program counter. Like it will be incremented and that will be stored in the program counter. We, like in our implementation, we do not have a separate module for program counter. Okay, we'll show you how we have done in the later weeks. Okay, so you can make a separate block for that as well. Okay, it's not a big deal. It's just a register. Okay, you can do that as well. There's no right or wrong in this. Okay, okay. You just got a basic view of instruction memory. Okay, and then what else? Okay, we forgot about the register file. Okay, yeah, let's look into the register file. So what were the input there? So okay, we having the clock as well. Yeah, okay. So what are the inputs that we are having? This is what we saw in the block diagram, right? I hope you all remember that. I just showed it to you. Where is that? There. See, read register. 1, 2, write data. Okay, let's check what we have here. Read reg 1, 2, write register, write data. So these are the inputs. Apart from that, we have the control signal reg write that we just looked into, right? From the control signal. So that also is an input to register file. Okay, whether we wish to write the data or not. Okay, and then the outputs is read data 1 and 2 that will be passed to the ALU. Okay, I hope that's. Okay, you'll get used to it. No need to feel overwhelmed. Okay, so what have we done? We've just defined 32-bit registers. Okay, 32 into 32-bit registers. Okay, so that is what we have defined. And for read operations, what have we done? Okay, the value that we get from the read reg, based on that we map to the corresponding register and then we are putting the value into this read data. That is what we have done. Okay, it's just a ternary operator. Okay, if it's 0, we return 0 because the 0 register 1 contains only 0. Okay, else we just give the value. Okay, I hope that's clear. Similarly for write logic, so at every passage we are writing the value. Okay, that's all. Okay, if you want to look into the test, let me just show you the test. Okay, register file dot test bench. Okay, so if you look into the test bench again, if you'll see, so these are the inputs. We'll be giving the values here and the outputs will be visible. Okay, so we're instantiating our register file, defining the clock, we're putting an initial block for the dump file, and we're giving the set of values to check if the read and write is happening properly. Okay, similarly you can go to the waveform and like follow the same procedure and check from the waveform whether it's working. You can also add a dollar monitor here. If you can just put another block and add a dollar monitor, you'll get the value get the values along with the timestamp. Okay, that's clear. So this was like the basic implementations of the blocks. Okay, so we just started building the data path blocks. Okay, I hope that is clear to you all. Yeah, so that is all was for this week. So see you all next week. Thank you. Bye.